Welcome to Lab 4 for Physics 2211. In this lab, we will examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We want to understand the fundamental principles involved in the system and how we can use them to create an accurate computational model that follows those principles. Once the fundamental principles are understood, we can observe and examine the video of the spring mass system, track it, and create an observational model based on that data. We will then create a computational model based on our initial conditions and compare and contrast that with our observational model, paying attention to the energy changes. Our fundamental principles are Newton's second law, which is change in momentum equals force times change in time. This helps us specify our forces to create predictions. The total net force is equal to the force of the spring plus the force of gravity. The second fundamental principle we are using is the energy principle. If we think of our system as the mass, the spring, and the earth, our surroundings are nothing, which means that no work or energy change is being done between the system and surroundings. Our change in energy can be represented as a change in kinetic energy plus a change in potential spring energy plus a change in potential gravitational energy. To create a complete model, we need to know two more things: the K, which is a spring stiffness constant, and the L0, which is a relaxed length of the spring. Based off the observed video data, we can use the period of oscillation to solve for K, which gives us 6.088 newtons per meter. And we can use our K to solve for the length of L0. We know that the gravitational force and the spring force are at equilibrium when the system is at rest. So we use this relationship to solve for L0, which is 0.1269 meters. To set up the computational model, I used the following conditions that came from the observational model: the mass, 0.402 kilograms, the period of oscillation in the y-axis, 1.5195, the spring constant, 6.87 newtons per meter, L0, 0.1269 meters, and L, 0.7 meters. I tracked the motion of the object for about 10 seconds and recorded the data points for the movement of x over time and the movement of y over time on a CSV file to compare to my computational model. I plugged in my initial conditions to the code: the mass of the object and the object's initial position, g, the spring constant, and the relaxed length of the spring. I created an equation to define L as the position of the ball minus the position of the spring, an equation to compute the spring force, and an equation to calculate the S. I also created equations to compute the kinetic energy, the gravitational potential energy, and the spring potential energy. For the net force calculations, I created more equations to define and compute the force of gravity, the spring force, and the F net, as well as equations for using Newton's second law to predict the new velocity and the new position. These lines of code update the spring. In these lines of code, I calculated all of the energy changes based on the previous lines of code. If we run the code, we can see our observed motion as a red ball and the predicted motion as a blue ball attached to the spring. We can see that the predicted motion and the observed motion lines up very closely. Here are the results of the x position data versus time and y position data versus time. The blue curves are the predicted data, while the red curves are the observed data. In the x position, we can see that the observed data slows down, and in the y position, it travels shorter distances as time goes on. This could be because I did not account for dissipative forces or for any loss in thermal energy. What does it mean? For my model system, is the energy principle satisfied? Yes. The total energy, represented by the yellow line, is zero, meaning all the energies cancel out. Our spring potential energy and gravitational potential energy are opposite each other, and the kinetic energy, which is smaller but oscillates at twice the rate as its other energies, cancels out the sum of all the other energies. What is the difference between the oscillation periods from the x and y axes? Using the data from Tracker, I can make two separate estimates of oscillation periods by using the y position data and by using the x position data. The x position data gives us an oscillation period that is 0.0195 seconds longer, but it results in a K that is 0.782 newtons over meters shorter and an L0 that is 0.0739 meters shorter. This L0 is significantly shorter than the L0 provided with the y position data, and I decided to use the L0 from the y component because there was more motion involved in it. That's all. Thank you.